We had a pot. All right, and I'm drawing it smaller today. So, when you had this pot yesterday, we said that in order for this pot to boil, what had to happen? This is important. All right, you just transferred from the bird to the water, yes. What else had to happen? Well, smaller molecules move faster. The water evaporates up here, yes. And it reaches and it touches what that's up here? The cold air. All right? When it hits the cold air, the water will do what? The water vapor will condense. Now, when the water vapor condenses, it goes back into the liquid state. The liquid state again is still being heated, so the water again starts to do what? It evaporates. Now, this water above the pot had a name yesterday. What was this water above the pot called? All right, the water vapor above the pot is called equilibrium vapor pressure. We're going to learn how to read a graph of that today, which is why I'm going back over it. Okay, it's called equilibrium vapor pressure. All right, now, when this continues to heat, what happens to that equilibrium vapor pressure? Does that pressure go up, down, or what? That's right. So as the water heats, the equilibrium vapor pressure goes up. Okay? As that water heats, the vapor pressure goes up. Now, the question I just asked you was, when does the water boil? Okay. The water does not boil until the pressure above the pot equals atmospheric pressure. I know. I'm reviewing it because every year I go over it, and every year people come back the next day, and I ask when water boils, and you go, I don't know. Just like today. I don't know. Okay? So this pressure continues to go up. Okay? As the stove heats the water, the pressure above the pot goes up. When that pressure equals what magic number? Atmospheric pressure, the water will boil. Now, this was the part we were talking about at the end of class with my ugly picture. Is all atmospheric pressure the same? No. No. So are all boiling points the same? No. So I drew a really ugly map of the state of North Carolina. Where is pressure higher? At the coast. So where is boiling point going to be higher? At the coast. So food cooks higher at the coast, the higher temperature. At the mountains or in the mountains, the atmospheric pressure is lower. So food will cook at a lower temperature. So on the side of like a baking box, it'll say at elevations of like 3,500 feet, you need to do what? Cook it longer. Usually it says cook it like 10 minutes longer because it's cooking at a lower temperature. If you only cook it for, let's say it said 15 minutes at whatever, cook it for 15 minutes in the mountains. If you only cook it for 15 minutes, will it be done? No, it will not be done. So it usually says to cook it for like 5 or 10 minutes longer because it's cooking at a lower temperature, it's not going to be finished. It is hot, okay? It's a lot like weight. Weight is the only thing that factors in weight is what? Do you remember?
Gravity.
Gravity. Weight and gravity are factors of each other. Math never changes. If I said to all the moon, your math will not change unless I get really, really angry and chop your heads off. I'm yelling out something just dumb like that. Okay? Now, if we go to the moon, we go to Jupiter, we go to Pluto, the only thing that changes those celestial bodies is their size, right? Yeah. So their gravity will change because their size changes. But our masses, when we hop from one celestial body to the next, will our mass change? No. But our weight would change because their gravity changes, right? Okay. So, me. Comes all the time.
Just like an example.
Oh yeah, thank you. Oh wait. If we're going to mountains, for example, let's say down here, Alexa, what do you weigh? 90 pounds. Alright, so let's say Alexa goes to a low mountain. She might weigh her 96 pounds here. She might weigh 94 pounds there. So let's say we send her out to the Himalayas. She might weigh 90 pounds there. The higher she goes in elevation, the farther she gets from the center of Earth, and there's less gravity, her weight is going to drop. Right? Right. And as you get further from the Earth, away from gravity, once you leave the gravitational field of the Earth, you become what? Wait.
I just know that.
No gravity.
I need to go to the mountains.
I need to go really high enough. Yeah.
They get harder.
It's hard to breathe for most of the air. Right, because the gravity is not as strong. The closer you get to the center of the Earth, the greater the gravitational force you weigh. You could weigh technically slightly. I mean, it's not really going to make that.
Yeah, but
it could make pounds over like a pound or so. Yeah. Yeah. Technically, yeah. Okay. Yes. Okay. Now, so if just saying, if we lower the temperature on this, what happens to equilibrium vapor pressure? It goes. Equilibrium vapor pressure goes down. So when you turn your stove off, you just let the water sit on the stove. The water cools. The vapor pressure does what? It decreases or goes down. Is everybody with me on that? Okay. So let's talk about a graph. Equilibrium vapor pressure graph. Now, this is the one that was on the back side of your homework the other night that I told you not to lose. Right? And this is a traditional graph. Works like every other graph you've ever read, except I have to teach you to read one point on the graph. Temperature is on X. Pressure is on Y. Typically, it's going to have a curve to it. If they ask you to read a temperature or read a pressure, it works like every other graph. So if they give you a pressure and they want a temperature, you read over to the graph and read down or vice versa. The problem is if they ask you to find, I think it's called normal boiling point. All right? If they want you to find normal boiling, write it all the way up. And a lot of times we abbreviate that NBP just because we're lazy. Okay? Anytime it says the word normal, and you're going to see that in a phase diagram very shortly. Okay? The word normal always means at standard pressure. Now, in order to do that, you have to check which pressure unit is being used. Sometimes it's atmospheres, which is nice and easy. It's always one. Sometimes it's KPA, sometimes it's TOR. You just don't know. I have seen millimeters of mercury, I've seen TOR, KPA, and ATM. I don't think I've ever seen PA used on a scale. So 1 times 10 to the 5th, I'm pretty sure I've never seen on a graph that has been used in a first year chemistry class. So I think you're safe from getting it. I got everybody caught up. All right, so I'll try and not done. Good evening.
Yeah, we're right. I know what
Everybody caught up?
Oh, yeah.
All right, so if I cruise back over here. All right, let's just say that this graph reads at atmospheres, which is the most common unit you're going to find. Not always, but let's just say this one is. So, if this graph is labeled in, let's just say 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4. Okay? What do you know is on the atmosphere scale? What's standard pressure? 1. Okay? You're going to find 1 on the atmosphere scale. You're going to draw in a line all the way across your graph. All right? So that is standard pressure. And you're just going to draw a line here. Now, that intersection right there is the normal boiling point. Always. You just draw a line in at standard pressure, and that intersection right there is the normal boiling point. So, how then do we find the temperature? You just read down and read whatever the temperature happens to be, and you have the temperature. Any questions about how we did that? Good. Find your homework from the other night, and I'm going to give you about 5 minutes up to find those answers before we talk about a phase diagram. That's it. That's more than I want to give you.
I wasn't still making homework, but it works better if we actually practice.
So this is like for
What's standard pressure is for?
oh, 7.
Yep, you draw a line with 76, and you don't have to estimate.
Just estimate.
Oh,
No, we need to do normal. Liquid B. They're going to be done. They're going to be done.
Should. Go off. Asking about that.
Oh, and I
I don't know. So which one have the strongest feeling like your family? How do you know? You got those, you got those. Why? What about? All right, so if you look at question one, all right, what temperature did you come up with? Again, these are estimates. Is this what asks for pressure? What did you say, Shatoria? Shh, hush. All right, what did y'all come up with so I can see my graph here? All right, well, okay, it gave us 400 torr. All right, so 400 torr, I'm just going to draw a line. And I'm not going to be any too straight here, but it's the best I can do.
Wait, 440?
And then it say that for the first one? Yeah, number one, so 400 torr. Temperature is going to be.
Oh, wait, I thought you were talking about.
No, I was trying to estimate. So somewhere in the mid 30s, about, I'm going to go 36 shifts, 37, 35, somewhere in that range. Okay? For B, somewhere. All right, that was terrible. Let me try again. All right, I'm going in the upper 60, 67, 68. Okay? And then I'm going around 100. That seemed to be a little skewed there. Maybe 98, 99, 97. Sounds good. If I look at my answer sheet, I had 97 when I did it on real paper with a ruler. All right. So, everybody okay on those? All of them, the unit is what? Degrees Celsius. All right. So if I get rid of that, and I put the temperature in this time for the next three, we have 35 degrees Celsius. So, there's 35. So, reading across for A, between 350 and 400. So, I had 370 when I did it on my paper. Looking at my line, a little higher than 350, 360 there. Okay. B, 180, 170. Okay. And this one, 50, 70, somewhere in that range. Okay? And all of those units would be what? Torr. And those will have a little more flux in the estimate because they're a bigger range. The what one? For number 4, I had 370 on my paper. All right, but you might have as low as 350 based on the way I have my line drawn up here with this pen. Okay? Now, number 7, you had to use standard temperature and pressure because I said normal boiling point, right? So what is standard temperature and pressure? So I've got to estimate 760 up here, so that's already, that looks a little low to me. Let me try again. Still looks a tad low, but my line's not straight either. All right, so trying to bring this down for standard temperature. Ooh, terrible. All right, so for A, I got somewhere in the lower 50s. So what'd y'all get? Mine looks around 52, 51. I have lower 50s. If I look at my key, I had 52 when I drew it on my paper. All right, for B, I've got somewhere around 81, 82. If I look at my key, I had 81 when I did it the first time. And for C, I have 110. Okay? Well, you could have a ruler. Now, the last one, strongest intermolecular forces. All right, strongest intermolecular forces equals highest boiling point. So, who has the highest boiling point on this thing? C. I tell you to figure it out. Whoever has the highest boiling point has the strongest intermolecular forces. Yes, ladies. You're stretching. You are too? Because y'all stretch not straight up, like out to the side. All right, question. All right. I think we're on the phase diagrams, if I'm not mistaken. We've done that. Yep, phase diagram. All right, so the last graph that we have not talked about that we need to do is the phase diagram. A phase diagram is one of those that's very easy to read as long as you learn the parts. All right? And that might be as far as we get today because it has multiple parts. All right, a phase diagram shows where a solid, liquid, and gas all exist on a graph based on temperature and pressure. Now, we're going to draw it. I'm going to freehand it. Some years I have people copy it. I've learned over the years it works better if I freehand it and label the parts. There are 1, 2, 3, 4 parts, 4 points that you have to be able to find. I would not draw it really small. I don't think it has to be half a page either. A third of a page would probably be acceptable, just because you're going to have to label multiple parts. And yeah, that's probably plenty, Nathan. All right, because we're going to bebop between the definitions and back to labeling the parts on the graph. Okay? Does everybody have the definition? Hurry it up. I need to turn the page. Everybody got it? All right. So, I'm going to draw mine so it fills the board just because I don't write neat and I'm going to mistake. All right, temperature is on X. Pressure is on Y. First of all, it's generally going to be some Y. The Y can vary. It doesn't always have to be exactly the way I've drawn it there, but it is going to be in some Y shape. In the Y shape, you are always going to have a solid here. The liquid will always be in the middle of the Y, and the gas will always be out here. Okay? Everybody with me on that? Now, these lines here always represent equilibrium. Now, the only thing that changes is equilibrium between what? Well, this line is equilibrium between a liquid and a what? Gas. So this would be equilibrium between what phases? Equilibrium between liquid and a gas would be what? Evaporation and condensation. So on this line, we would have evaporation and condensation. But down here on this line, we would have what? Sublimation and deposition. And up here on this line, we would have what? Freezing and melting. Okay? But those lines always represent equilibrium between the states. Everybody with me so far? Sublimation was changing from what to what, Tashawn? There you go. That was what he accused me of not teaching before or during the quiz. That's good. After you accused me of not teaching.
Wait, someone
I love the way you always jump to that conclusion during a quiz. Say what? Yes. Okay. Everybody okay with the part before we start talking about the 4 points you have to be able to identify? Okay. Everybody got it? Before I turn the page. All right. The triple point is the easiest one to find. It's also the easiest one to define. The triple point is the temperature. Is the point at which a solid, a liquid, and a gas all exist at equilibrium. To find, it is the point where the lines intersect. It is the easiest point to find on the graph. Nobody ever gets this wrong on the test. I had to make a guess, but probably not on the test. I think you might get lucky. Might be there. I'll never know. Because it's easy. I wouldn't put it there. Given I never had 100 on the exam, sure. Probably about 98. I don't remember. I'd have to go back and look. I've had lots of good grades on the exam, but 98 is it's tough to make a 98. I mean, I'll be honest. Even with the state curve, it's tough to get a high score on my exam. There's always a state curve on state test. I mean, the CTE has less of a curve than these do, but all science, English, math, there's always a state curve. I mean, if you got the score you actually made, some of y'all would be falling in the hallway if you got your exam score back. Particularly in math and some social studies class.
Oh, in math, absolutely. Honestly, as well, I haven't passed it out because I got the
Honestly, entirely possible.
It is entirely possible, and I think teachers have researched about the exam to like extract the whole and like.
Well, there is a pretty significant curve on some exams. We don't set the curve. That comes from the state or the central office. Some classes are curved more than others. I think the science classes have less of a curve, and it's a little more normal. But there are some classes where it is really out of hand. The chemistry class, honestly, is probably the one that is the least out of hand out of all of them that I've seen. The physical science is probably a little more inflated than y'all's, but y'all's is the least out of hand. Our science is probably more so than these. Put it this way, you can make a level 1 on the biology exam and still pass. on the test. That's what I'm talking about with it's inflated. If that gives you any indication as to how much it's curved.
Like, I never found that in time, but like, I still have to pass.
Yeah.
Like, there's two still possible ways. Like, I brought it back, fill it out, and then like, well, I'm just, okay.
Yeah, I still think it's going.
Still survive. Alright. The critical point doesn't have one definition. The critical point has two definitions. Alright? It's defined as the critical temperature and the critical pressure. Why that is? No idea. But no, I would have thought we'd have one definition and not two, but I don't know why. Okay? The temperature above which a liquid cannot exist. Right? The temperature above which a liquid cannot exist. Alright. So the critical pressure is defined as the lowest pressure a liquid can exist at the critical temperature. So they're sort of defined opposite of each other. And again, don't know why, don't ask me. Alright, but it's the lowest pressure a liquid can exist at the critical temperature. Now, again, I don't think I'll ask you definitions. How are you going to find this? This is always on the liquid vapor line. Okay? This is going to be on the liquid vapor line. It is either at the end, which is what you typically see, or it can be where the line goes straight up. It depends on the graph. Most of the graphs just end. So it will be the first one. The liquid vapor line is just end. It's that final end point. However, some graphs don't just end. They have a curve and then they start straight up. If that happens, it's the point where it starts to go straight up. Typically, you get the first. This is what you typically get. But I have seen some graphs that draw that way, so I'm pointing that out. Where, or it can, I got too many ifs.
Yeah.
Remember that if. Or it can be where the line goes straight up. It's a little curve, and typically when it curves and it curves different, a lot of times they'll draw a dotted line to show where it's going straight up. So it indicates it stops curving and it goes straight up. But again, it's still where it stops curving. It's still the end of what it's curving. Now it's roll up. All right, has everybody got it? All right, so if I go back, what color did I use? I used black. So let me use like a lime green. All right, so this is the liquid vapor line, right? So right here at the end, that is the critical point. Now, just to give you some idea of how it could look if they didn't draw it that way. If they had something different. Okay, right there at the end. See, I just drew a dot there. Don't graph ended, right? So if I cruise back over here to the way I drew this, I hope somebody landed with their head there. Okay. So if I have something like this, a lot of times what they'll do with the curve stop is they'll draw little dots at the end of it like this. Right there where it stops, see how they have those little dots there? Where it ends, right there, is where the critical point is going to be. It's before the dots are there, okay? Largely to indicate that that's where it starts going straight up. For those people who don't know, that's where it's going straight up. They're trying to say that's the wall, and everything past that point now is a what? It's a what? A liquid can no longer exist. So everything past that point is now a what? It's a gas after that point. Okay? All right. So the last point you guys have to be able to find is the normal melting point, freezing point, and the normal boiling point. Now, we already know that the normal melting and freezing point are what? We change from what to a what? And boiling point is a, so we only need to know how to find it. So how are we going to find it? What did we just learn about equilibrium vapor pressure? Okay, so you have to use standard. I'll be right to find instead of skipping that part. All right, draw a line at standard pressure. This one, it is the intersection with, this one will be the solid liquid line. Okay? So with boiling point, after we draw the line at standard pressure, this one is the intersection with what? With the liquid vapor line. But again, we have to draw this line in. All the way across the graph, just like we did with the equilibrium vapor pressure. All right, you all have it written down? Okay, we're flooding nice, but you know, look at one more part on that. Go back there and look at.
No, I got my own. Yeah, like, I need it. Like, I need to get it out.
All good. All right, so if we look at the graph, all right, what unit do you want to put on this graph? All right, so we put ATMs on the graph. All right, then make this one, make it a blue color. All right, so ATM. All right, let's just put one ATM here. All right, try to put it on your graph where it's not going to interfere with anything else. All right, so I'm going to put it here. And it is hard because I'm going to wind up with it in the way of my stuff. All right, so here's the dot, and there's the dot. All right, where my line went all the way across. So this intersection right here is my normal melting point, and freezing point. Okay, normal NP and FP, and this will be my normal boiling point. Questions about how I did that? Anybody? Yeah. Yeah, reading the graph should not be difficult.
It's a lot.
Just a lot to keep straight on the graph itself. So far we're up to 3 graphs. We have a 4th one to go tomorrow. There's the 4th one, the potential energy diagram. And all 4 graphs will be on the test. And I did tell you the test will most likely be after Christmas, right?
Yeah.
Okay. I just don't think with the weird schedule next week that we can do it.
We'll get a day before.
Huh?
We'll get a day before.
Yes, we will not test today we come back. So it would, we come back on the 3rd, it'll probably be the 4th. Okay. All right, everybody caught up. All right, let's talk a little bit about what we're going to do tomorrow. All right, tomorrow we're going to talk about collision theory. Tomorrow we're going to talk about collision theory and kinetics.
Mom?
Yes. Yes.
Mom?
Yes.
Can you send Emma West to the office? She's signing out.
Yes, I will.
Thank you.
Welcome.
No, I love.
Rudolph. I'm sorry. I'm so sorry. Yeah. You gotta cover when you put the ear.
Yeah, I think you should put it back on and, and wear them.
No, I don't know what I'm
laughing.
I will. I just think that.
No, I think it's cute. I'm glad to keep it today.
Bye, Emma. Hi. Oh, you know, that's the word whenever they're like, hi, my name is Nita. They're like, hi, Nita. Bye, Emma.
I'm Nita, I'm alcoholic.
Yeah, my name is Nita Vega. From and then I had this wall.
Where am I saying that at?
The support group. You know how like support group that like, hi, my name is Nita, and then everybody's like, hi, Nita.
Oh, okay. Yeah, I can do the support group someday. All right, so tomorrow we're going to talk about collision theory. All right, so what is collision theory? Any ideas?
How they collide.
Okay. All right, and we need a little more than that. Why are y'all packing up? We got time. All right. Not necessarily how they combine. Okay. All right, this is the premise. All right, yes. Molecules collide. And the more frequent the collision, I'm going to start doing twice here. All right, the more frequent the collision, the greater the opportunity for success. So we're going to talk about the 2 requirements, A, to be successful, and the 5 factors you need to increase the chances to be successful. So there's lots of things that are packed into tomorrow. First of all, There is no quiz tomorrow. The quiz will be on Friday.
And if you have missing work, I will be here today until about 4:15. I will be here tomorrow, which is Thursday. And Monday is the last day to make up any old crap that needs to be made up. So please, you're what I thought I gave, 3, 4. One for you, you'll make.
Oh, man.
Fine.
No, I'll take a picture of it. Pull out my phone.
Yeah. The quiz on Friday will be yesterday, today, and tomorrow. This is just a little bit of review, hodgepodge kind of stuff on the floor. Only there's a backside that apparently I forgot to put on. So you're doing both those sides, yeah. It's not long, it won't take you very long to do it at all. Let me hit stop on this.